Hello everyone, we want to talk about a quantity in physics that is called torque, and it happens to be a vector quantity, and that shows the relevance of our vector unit with the physics. So torque, or the other name for that, is moment. It is a quantity in physics, and I did search in some physics textbooks and calculus textbooks, different textbooks, to find out unique definition for torque, what it is. And in different textbooks, I found different definitions. They're all different descriptions for the same thing, but I selected two best of them. So it says a measure of the turning or twisting effect that an acting force has on an object. So a measure of the turning or twisting effect that an acting force has on an object. So we're not talking about you have some sort of box and you push it forward, for example, and it moves forward, having a linear displacement. We're not talking about that. It's not that kind of force that causes linear displacement. Like when you grab a piece of rope attached to a box and you pull the rope and the box comes with it. It's not that kind of force we're talking about. A measure of the turning or twisting effect that an acting force has on an object. So it is a force that has this sort of twisting effect on the object. Another definition was the turning effect. So a torque is the turning effect of a force, when the force causes an object to turn instead of changing in position or instead of having a linear displacement. Okay? The turning effect of a force when the force causes an object to turn, to twist, instead of changing in position. So that is actually what torque is. Imagine, for example, a door, okay, and you know where the doorknob is. When you are putting your hand on the doorknob and you pull the doorknob towards yourself, what is happening to the door in your opinion? Don't you see that the door is rotating about its axis, which is that pivot attached to the wall? So that is what is happening. So your hand, the force that is applied by your hand on the doorknob causes the whole door to twist or turn or rotate. And as a result, the door opens and you walk in. Same thing if you push the doorknob forward with your hand, then this force has a sort of turning effect on the object, which is the door, and it causes the door to close or to rotate. But I don't think that the door is pulled off the frame and starts having a linear displacement moving like 2 meters forward just because you are pushing on the doorknob. That is not happening with the force exerted by your hand. But what is happening is that the door starts rotating or turning or twisting about its axis of rotation, which is the pivots attached to the wall. So that's what torque is, the turning effect of a force. Okay? And the symbol we use to show this torque is tau, T-A-U. It's a letter from Greek alphabet. T-A-U is the name, tau, and it has this kind of symbol here, and we have a vector sign on top because it's a vector quantity, and that is equal to vector r times vector f. Now, what is vector F? Well, it's clear it's the applied force measured in newtons in system of SI units, SI system of units. And R stands for something we call it torque arm, or known as lever arm, and that is measured in meters. We'll tell you what that is. And tau would be the torque, and obviously because one is a torque arm measured in meters, the other one force in newtons, so the unit of measurement for torque would be newton meters, clearly. And this tau, this torque, is a vector quantity, and the type of product here is cross product, which comes from the vectors unit. So you see that physics and vector geometry are like two siblings. Things are related to one another. The cross product of the torque arm and the applied force is equal to the torque vector, okay? But what is this torque arm? Torque arm is actually a vector from where to where? From the pivot point, okay, to the point where the force acts, okay? So in the example of the doorknob, the point where the force acts is actually the doorknob, and the pivot is like the pivot of the door on the other side. This pivot, and it's attached to the wall, and the door is rotating about that axis. So that is the pivot point, and from that point to the doorknob where you're acting with your hand, you're applying the force. That distance, that vector joining those 2 points is actually what we call it the lever arm or torque arm. So that's vector R. Vector F clear, cross product gives you the tau. Now, what is the magnitude of this vector? Okay, every vector has direction, magnitude, unit of measurement. Unit of measurement for torque is Newton meters. The magnitude is actually the magnitude of this cross product, which by definition, again from vectors unit, we know it is magnitude of R times magnitude of F times sine of the angle in between these 2 vectors, sine theta. So that's the formula that comes directly from the definition from cross product of 2 vectors. And that's how you calculate the magnitude of this torque, okay? And so unit of measurement, magnitude, we talked about it, direction is left. So we said that torque is a vector quantity, so what is the direction? How do you determine the direction of this vector? Well, the direction of vector tau, the torque vector, is found by placing your right hand, so this is the right hand, on the diagram so that your fingers curl in the direction of rotation from R to F. So here we have a diagram. This is vector F, that's vector R. They're making an angle of theta. We have drawn them tail to tail. And it says use your right hand, put your right hand on the diagram so that your fingers curl in the direction of rotation from R to F. So I put my hand like this, and my fingers are curling from R towards F, as you see. Okay, so from R towards F. Your fingers curl in the direction of rotation from R to F, so from to R to F, like this, through an angle less than 180 degrees. Okay, through less than 180 degrees. The thumb points in the direction of the torque vector, and this is known as right-hand rule. So right now, I'm putting my fingers in the direction of R and curling them through an angle less than 180 degrees to reach vector F, and you see that the direction of thumb, which is outside the whiteboard right now, or it's upward as it says here, that's the direction of the torque. So the turning effect that torque is going to have, it's going to be in this direction, outward, out of the page in your case, in your notebook. In my case, out of the whiteboard. But if R is this way, so if I hold my hand like this, I can't curl through an angle less than 180 degrees to reach F. So I'm obliged to do what? To hold my hand like this, and so yeah, I have to. It says from R to F. Okay, so okay, R to F. So this is R right now. Okay, curl the fingers through an angle less than 180 degrees. This time it's this time it's an obtuse angle, but still it's less than 180 degrees. So R to F, if you curl your fingers from R to F, the direction of the thumb, which is into the whiteboard, will be the direction of the torque vector. So here, R to F is like this. The thumb direction is upward. It's coming out of the whiteboard. In this case, it is going into the whiteboard, okay, because the direction of the thumb is into the board. So this is another example of application of torque. It's used in tightening of a bolt. You have a bolt here. This is a wrench, okay, and we want to tighten this bolt. How do you tighten that? You apply a force on the handle of the wrench, and this force is being acted at an angle of theta degrees with the vertical, for instance. And where's the center of rotation? Where is the pivot point? Well, it's the center of the bolt right there. And from there up to the point where you're acting your force, somewhere here it says the point where the force acts is right there. So this vector from the pivot point up to the point where you exert the force, that is what we call the lever arm or the torque arm. That is your vector R. This is your vector F. And when you apply this force F, so this is R. If I draw them tail to tail, how would it look like? Yeah, it would look like this. So if I draw this tail to tail, it's going to be F this way, okay? And R is, of course, to the left. R is like that. So this is F, and that is R, okay? And they're making an angle of theta. So theta here is this angle. So that would be, with this direction, that would be 90 degrees minus theta. But that doesn't matter. R is that way. I'm curling my fingers towards F. And you see that the direction of the thumb is into the page, into the whiteboard. And that means that when you exert a force F here, in this way, you are actually tightening the bolt because the twisting effect of that force causes the bolt to go inside whatever mechanical system there is. Maybe you got a flat tire and you want to tighten the bolts, or you want to loosen them up to just change the tire of your car. Who knows? So if you want to loosen the bolt, let's say to change the tire, flat tire, then you have to exert a force like this. So you have to exert upwards. So in that case, R to F, F would be that way, and R to F would be cause the torque to be in the direction of out of the whiteboard, which means that you are actually loosening the bolt up and the bolt comes out, okay, as a result. But right now, as it is, you are actually tightening it, okay, and the bolt goes inside. So it's the turning effect of the force that is being applied. And as I said, the direction could be into or outside the board. I hope this summarization is good enough, and it explains what torque is briefly in terms of formulas, in terms of type of quantity, which is a vector quantity, in terms of the direction and all that. And numerical examples will, of course, follow later. Thank you.